Welcome to a chemical kinetics screencast. This screencast will go through an example of the calculations for a first order reaction. The example deals with the decomposition of sulfuryl chloride, SO2Cl2, to sulfur dioxide, SO2, and chlorine gas, Cl2. This reaction, the rate law is found by experiment, of course, and it's found to be a first order reaction. And we also have some data. It's found that it takes 11.6 hours for 0.250 moles of SO2Cl2 to decompose to 0.1 mole of SO2Cl2. And this is at 320 degrees Celsius, and we're in a 1 liter flask. And several parts here: write the chemical equation for the reaction, write the rate law for the reaction, state the value of K, or determine the value of K for this reaction, the rate constant. Find the rate of decomposition when SO2Cl2 concentration is 0.15 molar. Find the concentration of SO2Cl2 after 24 hours. Find how long it takes for 95% of the SO2Cl2 to decompose, and then find the half-life for the reaction. So multiple things to determine for this particular first order reaction. First of all, the chemical equation. This is just a Chem 1A translation of words into equation, and hopefully this is pretty straightforward. SO2Cl2 decomposes to SO2 and Cl2, already balanced 1 to 1 to 1. The rate law, since this is a first order reaction, the rate law will be rate equals K times SO2Cl2 concentration to the first power. So pretty straightforward and easy so far. Now what about the value of K for this reaction? Well, note that we have this relationship or equation. We know it's a first order reaction, so we know that equation. And since it's first order, we have the following equations or relationships as well. This ln of SO2Cl2 at time t equals negative K times t plus ln of SO2Cl2 at time 0 is the equation we've used for graphing. Gives us a straight line if we graph time versus log of concentration. And then a different form of the same equation in exponential form rather than logarithmic form is as shown. So which equation of all these should we use? And of course, the last two equations actually contain K, so we can solve for K. The reason we don't use the rate law is because even though that contains K, we don't actually know the rate. But we do know the concentration of SO2Cl2 initially and at a later time. So this is solvable using, it's solvable for K using either of the last two equations. So we'll choose this one just to show how you mathematically manipulate and solve this for K. Usual thing is you're getting everything else on the other side of the equation and isolating the thing you want to solve for, which in this case is K. So divide both sides by A at time initial or time 0. Then take the natural log of both sides, which undoes the exponential. And then ln of A at time t over A at time 0 is equal to negative KT. And divide both sides by t and of course a negative, and that lets you solve for K. Now it's time to plug in values, and if we take the equation we just solved for K and plug in that initially we have 0.250 moles per liter of our SO2Cl2, initially 0.25 moles in a 1 liter flask. After 11.6 hours, we have 0.100 moles per liter of SO2Cl2, 0.1 mole in 1 liter flask. And then if we do the math on this, what we end up with is 0.0790 per hour is the value for K. Part D, what's the rate of decomposition when SO2Cl2 concentration is 0.15 molar? And again, we have these relationships, And in this case, the best equation to use is the one that actually has the rate in it, since we're solving for rate. So we'll use the rate law. Rate equals K times SO2Cl2 to the first power. And note that we now know K, so we can do this. Rate is equal to that equation. K is 0.0790 per hour. So we plug in our values, and notice that when we multiply our numbers, we have units of molarity times units of per hour. So we get units of molarity per hour, and it's 0.0118 molarity or moles per liter per hour. Rates will typically be in concentration or some other measure of amount, could be pressure, and then per time. In this case, it's hours. Okay, part E. What's the concentration of SO2Cl2 after 24 hours? Once again, we look at our equations that we have, which is going to allow us to solve for concentration at a certain time, and that's going to be one of our latter two equations, and the one that's easier is the exponential form, because that explicitly has the SO2Cl2 concentration at a given time. So this will be the easiest equation to use. So to find the concentration, we now plug into our equation. The values are, we start with 0.250 molar of SO2Cl2. After 24 hours, that's our time. And we used K as 0.0790 per hour, which we found previously. And this gives us 0.0375 molar for our concentration of SO2Cl2 after 24 hours. F, how long will it take for 95% of the SO2Cl2 to decompose? Once again, we look at our possible equations and see which one's going to be the best to use. And if we're trying to find how long it will take, that's a time. So we're going to solve for time in one of the two equations relating concentration to time. And either one, when you do that solving for T, you get -1 over K times the natural log of the concentration of SO2Cl2 at time T over the initial concentration of SO2Cl2. There's our relationship. And now note that we have slightly different information than we've seen in the past. The question is, how long will it take for 95% of the SO2Cl2 to decompose? And we note that if 95% of it has decomposed, we have 5% left. And the reason we want to do that is because this quantity, SO2Cl2 at time T, is our concentration or amount at that is left after a certain amount of time has passed. Therefore, if we plug our numbers in here, K is 0.0790 per hour as before, and then we could figure out our actual concentrations if we wanted to, but if we start with 100% of SO2Cl2, then after 95% of it has decomposed, we have 5% of it left, so the ratio is 5 over 100, and plugging in gives us 37.9 hours for the amount of time it takes for 95% of the SO2Cl2 to decompose. And then the last part of this question is, what is the half-life for this reaction? And first of all, what is a half-life? The definition of a half-life is the time that is needed, or the time required for half of the substance to react. And in this case, since we've been just solved an equation for time, now we want the amount of time it takes for whatever amount of SO2Cl2 we started with, to end up having half of that. And so the half-life is typically symbolized T sub 1/2, and that will then have 1/2 of what we started with is how much we have left at the half-life. So this is the general relationship for half-life for a first-order reaction. And if we now plug in our values, K as before, and then again, whatever quantity we started with, we have half of it left. So it'll be the natural log of 1/2. and we get 8.77 hours. And note that this is going to be a constant value regardless of how much we started with, but this is only true for a first order reaction. And last note is that a first order reaction has a constant half-life that's characteristic of the reaction, of course at a constant temperature, but other reactions have variable half-lives. And that's it for the first order reaction calculations screencast.